Hey guys, welcome back. We're moving on into the next chapter. In case you're wondering, I've decided that we're not going to do the confidence intervals quiz. Instead, we're going to do a quiz right before spring break. So our last day in person over hypothesis testing. So we'll kind of incorporate all of that together in one quiz. It'll be a little bit easier there. Also, you might notice that I put grades in. So if you're missing the probability test or the probability quiz, those grades should all be in there. Then all the grades for what we've been doing in the last chapters for this new unit, Unit 5 over hypothesis testing, all of those grades will be put in right when we take the test or the quiz over spring break, right before spring break. All right, so we're going to move into this next chapter. It's really kind of just repeating everything that we've talked about before with hypothesis tests and confidence intervals, except now it's just going into a little bit more depth with alpha levels, p-values, and also the power of the test and the effect size, which is some really cool stuff. And then we're going to wrap it up next week in person with our M&M lab, which is going to be a ton of fun. So looking forward to that. I decided I was going to start giving you guys the page numbers. So I'm lecturing over page 516 through 523. I highly recommend, I'm giving you the highlights, kind of visually bringing it to life for you, but I highly recommend going through and reading those pages. It's the same examples that we're talking about here in the video, but you can go back. It's kind of like reading a transcript of what I'm saying, because it's just better to actually be able to read it in some cases, and you can go back and read it slower, go back and reread the paragraph if you need to or anything like that. Okay, so I really recommend, if you really want to understand this stuff, read the book. That's what I did a few years ago, and I still read the book just to make sure I got everything down. All right, so let's go ahead and get started. In 2000, Florida changed its helmet laws. So previously, if you were over the age of 21, you were still required to wear a helmet, but in 2000, they decided if you were over the age of 21, it was no longer going to be illegal for you to not ride with a helmet. So I wanted to let you guys know I used to be cool. I used to ride motorcycles, and I sold it and got a car, and I've aged, and craziness is behind me. But I always wore a helmet, except like one time going around the neighborhood because I was too lazy. But anyway, I was doing a test drive just to make sure everything was running right. But anyway, always wear a helmet. It's a good idea, definitely. Okay, so what happened? In 2000, they changed the law, so if you're over the age of 21, you no longer had to wear a motorcycle helmet. Well, people who were definitely upset about this law, they thought it was moving in the wrong direction towards less safe but more freedom, so kind of a trade-off between those two. And they were afraid that if people were given the opportunity or the freedom, it was no longer legal to not wear a helmet, that they would see a drastic increase in the number of people who were not wearing helmets. So what they wanted to make a study. If they believed in the year 2000 that when the law passed, or before the law passed, because it passed, I believe, in the end of the year, they believed that up to that point, 60% of motorcycle riders wore their helmets. And so then they collected data over the next 3 years, and in order to test the hypothesis of whether or not the data suggests that it's changed, that it's dropped. So they changed their laws. They believed that it was 60% of people that were wearing helmets in Florida. So the first question is, we want to draw a random sample, and we want it to be random so that's representative, right? But what would your sampling frame be? Remember, your sampling frame is your list that you're drawing your sample from. So all registered voters, if it's a political thing. But what is there a list of every person who rides a motorcycle in Florida? Where could you find a list of people who ride motorcycles? Well, you could call motorcycle clubs, or visit a motorcycle club and then survey people there. Okay, but what if would that be really a representative sample? Is every motorcyclist a part of a motorcycle club? Would certain motorcycle clubs kind of have some sort of group think where they all ride together, and it's some of them are very much anti-helmets and some of them are very safety oriented and they all wear helmets? And so you're probably going to have some group think that's going on between those groups as well. And what about riders who are not part of a motorcycle club? So what about, is there a list of all the people, like with driver's license, that have a motorcycle endorsement, that have an M for their motorcycle endorsement? Well, if we did have that list, that would be perfect, right? If we take all the people who have motorcycle endorsements, but what about people who ride motorcycles without a license, and then clearly they would be without a motorcycle endorsement as well. So that would be an underrepresentation, right? Because they wouldn't be included in that group. So then the question is, if you called up these people and you asked them, do you always wear a helmet? I admitted to you that one time I didn't wear a helmet, which probably shouldn't say that, but you get the idea, right? Are they going to lie to you? Is it response bias, right? Are you asking people to incriminate themselves? It depends on who's asking the question, right? Or whether or not they're going to be afraid to tell you the truth. So what we need to do Something else. So there was they decided they were going to look at police reports of accidents or involving a motorcycle, and the police, they have in their procedures, they would, if there was a motorcycle involved, they would always record the age of the age of the cyclist, of course, and also whether or not they were wearing a helmet at the time of the accident, right? So they looked at the accident reports from the next 3 years, so 2001 through 2003. And now this is not random, right? So we didn't randomly sample, it's just the people who were involved in accidents. But would we expect the people involved in accidents to be a representative sample of all the people who were on the roads riding motorcycles? So here we might have some, is it independent, in other words, right? So people who don't wear motorcycles, are they perhaps more reckless and also therefore more likely to get involved in accidents? So would we expect this proportion to be over-representative of the population that doesn't wear motorcycle helmets? Is there a different way of doing this? Could we look at camera footage on a turnpike or a highway and then look at all the people going through, sort them with AI or something, which sounds kind of creepy, but sort them, and then all the motorcycles, and look at whether or not they're wearing helmets? But that would only be that one place and that one highway or turnpike, right? So not all the small roads and stuff like that people might be commuting to work without using the highways. So it's kind of a good point to look at. So it's not going to be random, but is it representative? Let's just assume it's representative and see what we get. So now that we've decided how we're going to gather our data, we need to go ahead and write our null and our alternative hypothesis. So if you remember, our null hypothesis is going to be based on the fact that we believe there's no change. So that's going to be kind of like the status quo, okay? So in this case, we're going to assume that it has not changed and that the rate of people wearing motorcycle riders wearing helmets is still 60%, and that the law didn't change the rate or the perception of the importance of wearing a motorcycle. All right, then our alternative is going to be what we're actually trying to gather enough evidence to prove, right? So it's like innocent till proven guilty. So we start out with this this idea that it stayed the same until we have enough evidence to prove that it is actually changed. Now, what change are we looking for? Is it a one-tailed lower where we're looking for if it's gone down, or is it a one-tailed upper to see if the rate of helmet usage has gone up, or is it a two-sided or a two-tailed test where we would be interested to know if it changed at all, if it had gone up or gone down? Well, in this case, we're specifically trying to decide if there's evidence that it's gone down. Has this new law changed people's perception of the importance of wearing motorcycles? Are people abusing their freedoms now, etc.? Or do people still think it's important to wear a motorcycle helmet? Okay, so this is actually going to be the one we're going to use as the one-tailed lower. So we're interested to see if it's gone down. So then the next question is, what should we select our alpha level to be? Should it be 1%, should it be 5%, or 10%? All right, so when we're selecting an alpha level, we need to select it's going to be 1%, 5%, or 10%. Now, typically our default is kind of 5%. And you can read in the book, there's actually a cool little story about Dr. Fisher and how we got to the 5%. He just wrote it in a book once, and then everyone kind of took it as if it was sacrosanct, which is like saying as if it was like gospel, like it's the number we need to be using. Or are we doing a 1% significance level, which would be a higher burden of proof, or 10%? Like if we're dealing with candy, it's not that important if we're right or wrong. If we have a type 1 error, it's okay. We can do a sloppy 10% in this case. All right, so we're just going to default to 5% in this case. So remember, the type 1 error is the chance that we reject a true null hypothesis. So if it really is 60%, then as our samples are varying, 1% or 5 or 10% of the time, we would get in the lower 5 or 1 or 10% of the time, that could still happen. Now it's unlikely to happen. It's unusual, right? But it still could happen. And so even though we have to select a certain burden of proof, it still is not going to change the fact that we could be the 1% of samples where it just so happened to be, it's still 60%. We just so happen to sample values that were that low. Okay, so be careful with your alpha level. I mean, understand that even though it's unlikely that it could happen, the 5% of the time, it would still happen even though the null hypothesis was true. And we call that a type 1 error. So what was our sample proportion? So of the 781 accidents involving motorcycles in Florida over the next 3 years, 2001 through 2003, the police reported that 396 of those cyclists were wearing a helmet, which would be 50.7%. Now that's lower than our 60% that we believed were wearing helmets in 2000, But could this be just occurring by random sampling variation? Because we know samples vary, especially small samples, they vary a lot. So could this occur by chance, or is it statistically significant? So we need to look at the sampling distribution model centered at the null hypothesis, or the hypothesized proportion of 60%, given a sample size of 781. The standard deviation of our samples, of all the samples, is going to be given by the P naught times Q naught divided by the N, and we take the square root of all that. So our P naught and Q naught is going to be the hypothesized proportion, which is 60% and 40%, and then the N is our sample size of 781. When we put that in the calculator, which is a standard deviation of 0.0175. So then we can fill in the rest of our sampling distribution model by adding and subtracting that to both sides. We really only need to subtract it because we're only interested in the lower side, the lower tail. Then the next question we have is, where does our sample, so by the way, that would be a normal model, right? Centered at 0.6 with a standard deviation given there. All right, so the observation we had was 50.07, right? And if we look at that, that's going to be way beyond 3 standard deviations. In fact, I think it's about 5 or 6 standard deviations below the mean, which would be incredibly unusual. And if we want to find the p-value for that, well, we can actually put this in the calculator, which is kind of cool. So we're going to go to stat, arrow over the test. This is a 1 proportion z test. The hypothesized proportion, or p naught, is going to be 60%. And we found 396 out of 781. And we're interested to know if the proportion is, not that it's not equal, which would be a two-tailed, but that it's strictly lower than the hypothesized proportion. So is it less than 60% now? Then we hit calculate, and that will give us, yeah, so our z-score is negative 5.3, so it's 5.3 standard deviation below the mean. The proportion, sample proportion was 50.7%. And that's pretty much what we need. Now, the p-value is the 5.7 something times 10 to the negative 8 power. So that's going to be our p-value. Now, that is really, really rare. That's a really low value. And keep in mind, this is actually way, way out here, 5 standard deviations out there. So if we look at the area under the curve, you're not even going to see it. It's basically 0. Now, I'm going to show you how you can actually find this. If we have p-values that are really, really low, it's kind of hard to interpret them. It's practically 0 statistically. We could call that a statistical 0. So what I'm going to do is I'm going to go to variables and then down to statistics and then arrow over to test, and the p is the p-value, and then I'm going to take the reciprocal of that, which is 1 over the p-value, and that's going to tell me the probability of this occurring, which is a 1 out of 17 million. See if I got that right. Yeah, 1 out of 17.5 million. So you're saying there's a chance. To quote Lloyd Christmas from Dumb and Dumber. Was all that 1 in a million talk? Anyway, so you're saying there's a chance. Yes, it still could happen, but that's highly, highly, highly unusual, and I don't think that it happens. Statistically, this is not going to happen. So what's the probability that if this was a true hypothesis, if it really is still 60%, and the change in the helmet loss did not change the behavior of motorcyclists, what's the probability of getting a sample proportion that low? Well, that's like 1 in 17.5 million, which is so rare that we have enough evidence to reject the null hypothesis. We believe the true center of the distribution, which would be whatever the true proportion is not going to be 60%. It's going to be less than 60%. The next question that we might have is, what do we think the actual true proportion is? Well, now that we've rejected the null hypothesis in favor of the alternative, which is that it's less than 60%, now the natural thing to do is to write a confidence interval. So we're going to go to stat and then arrow over to test. And then we're going to do a 1 proportion z interval just towards the bottom. That's already calculated for us. If we were doing a 5% alpha level one-sided, then that corresponds with a 90% confidence level, but you could change it at this point, it doesn't really matter. And then we hit calculate. So now that we've rejected the null hypothesis, we can write a confidence interval and say that we are 90% confident that the true proportion, now after the law has changed, of motorcyclists who wear their helmet is anywhere from basically 48% to 54%. And if you notice, 60% is not contained within this confidence interval. It's not even close, right? That means that we are 90% confident that it's between the true proportion is somewhere in here, and we were able to reject the null hypothesis with the significance level of 5%. We would also probably conclude and just give them the p-value at that point. So you can do hypothesis testing with confidence intervals like we saw in the last video, but it's actually more precise to give the actual p-value of whatever we had, the 1 in 17.5 million All right, so now that we know it's gone down, that's what we think it's gone down to. But you would also still have to ask the question of, if you're looking at people who were involved in accidents, are they involved in accidents because they're less safe, and that means they're also less likely to wear a helmet, or because they know they're going to do stupid stuff, they're more likely to wear a helmet? I don't know. I have no idea. I think age has something to do with it too. All right, alpha levels, significance level. So this is the threshold. The p-value must, basically the burden of proof, determines when we reject a null hypothesis. So unless we have a p-value less than the alpha level that we set before we calculate the p-value, then we would fail to reject the null hypothesis. So it's only if it's in the top 5, 1, or 10% of samples that we would actually, if the null was true, that we would be able to reject the null hypothesis in favor of the alternative. But keep in mind that the alpha level is the exact same as the probability of a type 1 error, which is the probability that we falsely reject a null hypothesis when we shouldn't have. So saying that it could have actually still be 60% of people wearing helmets, we just thought that it had gone down. So I don't think with the p-value that we got that we have any issues with that. All right, the other thing is statistically significant is not always the same thing as practically significant. So if we have a large enough sample, we could detect even a 1% drop in the proportion of people who are wearing helmets. But if it had gone down from 60% to 59%, even though with a large enough sample that could be detected and it would be statistically significant, that might not be practically significant for overall purposes. For instance, if that was the overall trend that it had been going down before then we wouldn't be able to say that the law itself was the thing that changed it and that it's that much of an issue, or whether or not we should be looking at fixing the issue through some other means. All right, so let's go ahead and start the assignment. So example 1, a report on healthcare in the U.S. said that 28% of Americans have experienced times when they haven't been able to afford medical care. A local organization randomly sampled 801 Oklahomans, of whom 38% reported to have had times when they haven't been able to afford medical care. Does this indicate that the problem is more severe among Oklahomans than it is the national 28%? So is it possible that the sample we found in Oklahoma is actually just varying by random sample variation, and that the true proportion in Oklahoma is actually 28%, just like it is nationally? Or does this sample show us that we have enough evidence to suggest that Oklahomans are having more difficulty affording health care over the national proportion? So our null and our alternative hypothesis, our null is the status quo, or that there's no change, which would be that Oklahoma's proportion is the same as the national, which is 28%. So that's going to be that the proportion, the true proportion of Oklahomans who struggle with affording medical care is actually 28%, which is the same as the national level. The alternative is going to be, we're interested in seeing if it's actually higher, so that Oklahomans are struggling or are having more difficulty affording health care than the national. So we would do a one-sided or a one-tailed upper test. So we want to know strictly, is it larger than 28%, the true proportion? Next thing we need to do is select the alpha level. We're going to default to the 5%. This isn't like a matter of life and death, like death row or life sentences, and it's not like we're dealing with candy. This is fairly important. So we're going to select an alpha level of 5%. Check the necessary assumptions. So was it a randomly sampled? Yes, it was. So there could be other issues. I mean, how do they select their sampling frame and stuff like that? But from what they tell us, it looks like it's good. It was randomly sampled, so this 801 Oklahomans should be representative of all Oklahomans. That's certainly less than 10% of all Oklahomans, so we're good. Even though we're sampling out replacement, we can override the independence assumption with a 10% condition. Success failure, 38% of 100 or 801, bad dyslexia, is certainly more than 10 successes and 10 failures. Perform the mechanics of the test, find the z-score and the p-value. That's all going to be done in the calculator. So let's do it. So stat, let's arrow to the right to calculate. We're going to do a one proportion z test. Sorry, it's just right there, the fifth option. We found, our null hypothesis is going to be 28%. Our sample proportion, they told us it was 38% of 801. So when we calculate that, this was a rounded value, so we need to go to the nearest whole person, which would be, because you can't have a fraction of a person. And then the total that we had was 801. We want to know strictly if our proportion is greater than the national average. Then hit calculate. This will give you your z-score, which is 6.227 standard deviations above the mean, which is very unusual. because it's beyond 2 standard deviations, right? But not just looking at it as being unusual, we need to look at the p-value. So our p-value is 1.77 times 10 to the negative times 10 to the negative 10 power, which means there's 9 zeros in front of that. So the probability of that occurring, I can actually do that again. If I just hit this, it'll update it with a new value, by the way, which is really cool, is a probability of 1 in 1,000 million 5 billion, if I did that right. Yeah, so that's like 1 in 5.6 billion. Very, very, very rare. So that is overwhelming evidence that this is statistically significant. There's no way, statistical zero, right? There's no way that we would be falsely rejecting the null hypothesis, right? So if Oklahoma's average was 28%, just like the national average, there's no way, if this was truly a random sample that's representative, that the true proportion of Oklahomans struggling to pay for healthcare is the same as the national average. So we do believe, with overwhelming evidence, that there's an issue where Oklahomans are more adversely affected by whatever we're talking about with healthcare than the national average. All right, so perform the mechanics of tests. Basically, if we had 28% was the same, you can find the standard deviation kind of doing our formal models. The probability of that occurring is way, way, way 6 standard deviations above the mean, which is very, very unusual. And so what was our p-value? We'll write that down as well, which is the same thing I showed you before. And I'll go back to it. So stat, 1 proportion, z-test, all this is still the same. There we go. So our p-value is 1.78 times 10 to the negative 10th power. All right. Carefully explain what the p-value means in context. So remember, p-values are conditional probabilities. It's saying if the Oklahoma proportion is the same as the national average, so if the null hypothesis is true, then the probability of observing a statistic like we did or more severe is 1 in however many billions, 5.6 billion. Okay. So essentially, if it really was 20%, if the true proportion was 28%, which is the null hypothesis is true, then the probability of observing a sample of 801 with a probability of 38% is 1.5 times 10 to the negative 1 times 10 to the negative 10 power, or you can write an engineering notation as e to the negative 10 like the calculator does. All right, so what's our conclusion? Because our p-value is less than any reasonable alpha, and even certainly our alpha level of 5%, then we have enough evidence to reject the null hypothesis in favor of the alternative. So assuming the rates were the same, assuming that the null hypothesis is true and that Oklahoma is 28% just like the national, then practically a statistical 0% of samples would be this high. That is statistically significant at any reasonable alpha level, so we have enough evidence to reject the null hypothesis. Was our test a one tail upper, one tail lower, or two tail? We were just looking at the one side to see if the proportion was greater. So this would be a one tail upper test. Why did we choose the test we did? Because we were only interested in showing if it was worse in Oklahoma than if it was better in Oklahoma, then yeah, it would be something to be happy about. We wouldn't need to look at new legislation or something like that. All right, we wanted to see if the rate was higher. Another way of saying it. All right, number 12, another p-value. So have harsher penalties and ad campaigns increase the seatbelt use among drivers and passengers? Observations of commuter traffic failed to find evidence of a significant change compared with 3 years ago. So it still might have gone up. We just didn't have a large enough sample, or the effect size wasn't big enough of a difference for us to be able to detect it with the size of a sample that we had. So we're at the appropriate hypothesis. The null is that it's going to be the same. So we're going to assume that it hasn't changed until we have enough evidence to suggest that it actually has gone up. Hopefully because of the ads or whatever harsher penalties or campaign that we were running. So they didn't tell us the proportion, but whatever the proportion was, the percent of seatbelt drivers is still the same. Okay. The alternative is we're wanting to know if it's gone up, not just if it's changed, but strictly has it gone up, has it improved? Because we spent money on the campaigns and passed harsher penalties or whatever. So hopefully, if we have harsher penalties, then we at least have the benefit of the more people wearing seatbelts. So has it been effective? So has it increased? Has a percentage increase? Explain carefully what the study's p-value of 0.17 means in context. So 17%. So remember, p-values are conditional probabilities if the null hypothesis is true. So if it hasn't changed, then the probability of seeing the observation that we saw or more severe would be 17%. Now 17%, that still is kind of showing, hey, it might be moving up, but it wasn't just enough evidence for our sample size to get the p-value to be lower than 10%, 5%, or 1%. So we just fail to have enough evidence. So this is actually kind of what happens quite often. If you think even in a criminal case, right? If you watch like Dateline or 2020 or something like that, there are times, well, usually they probably don't make shows about it because it kind of freaks people out, but there are often times when they have a lot of evidence. It really looks like this person did it, but they don't have beyond a reasonable doubt. They still have reasonable doubt. And with 17% of it, it's a 17% chance this could be an innocent person. That's not enough for us, even though, man, there's a lot of evidence. I mean, we got this, and this. There's a good chance that he did it, or she, but we're just assuming violent crimes. It's probably a dude. Then it's kind of funny, but it's true. There's a chance that they're actually innocent, and if there's a chance that this could have occurred by chance and just random sampling variation, then we can't put somebody away for life and separate them from their family because of that. And so honestly, there's a lot of times that we fail to be able to reach the burden of proof of beyond a reasonable doubt in a criminal court. Now we might still be able to sue them and hold them civilly liable, where we sue them out of their existence. Then they write books and make money on it, just like that one guy did, O.J. Simpson. All right, which is a reference I shouldn't even get. That happened before I was born, I'm sure. All right, so what does it mean in context? I suppose I should show you that. So if the null hypothesis was true, then there is a 17% chance of observing a sample proportion or better than they did, which was not beyond our significance level of 10%, 5%, or 1%. So it wouldn't matter. All right, number 14. Environmentalists concerned about the impact of high-frequency radio transmissions on birds found there was no evidence of a higher mortality rate among hatchlings in nests near cell towers. They based the conclusion on a test using an alpha level of 5%. So discuss how they came to the conclusion. So the p-value was higher than the alpha level, right? So they found the probability of this occurring was more likely than 5%. It wasn't just in the top 5%. So they didn't have enough evidence to suggest that the high frequency radios were increasing the hatchling fatalities or something like that. So the p-value was higher than the alpha level, so the observations were not statistically significant. Would they have made the same decision if they had an alpha level of 10%? Well, 10% is less than, or is bigger. It's a lower burden of proof, right? It's a higher significance level. It's kind of weird because we're kind of working backwards at this point. So a higher burden of proof is a lower number, if you get what I'm saying. But a alpha level of 10% is sloppier than 5%. Is a good, I guess, one way of saying it. And so if our p-value is between 5 and 10%, then yes, now we would have enough evidence to reject it. So we don't know. The only way we would know is if the p-value is between 5 and 10%, then we would now be able to reject it, where we weren't able to with the higher burden of proof of 5%. All right, what about an alpha level of 1%? Well, 1% is an even stricter burden of proof. Instead of saying higher or lower, it's probably better to say stricter or looser burden of proof. Whatever. So this is an even stricter burden of proof, or stricter significance level. So if we could reject it with 5%, we certainly can't reject it with 1% now. So they would still reject it with a higher or more significant alpha level of 1%. All right, so that's it. If you have any questions, please make sure you let me know. Can't wait till we come back in person and I can see you guys again. I guess it'll be tomorrow because I'm recording this Sunday night. Also, next week in class, we'll be doing our M&M lab. So if you guys are at home, get those M&Ms. See if you can keep them without like opening them. But if you do open them, just make sure you count them and sort out how many orange ones you got out of total. And then we'll input that data next Monday and next Thursday whenever I see you guys in class. It's going to be super cool. Can't wait. And you can do it a fun size bag M&Ms. You can use any size M&Ms, even like a massive bag if you want to buy like in bulk. That sounds good. Just don't eat them all in one sitting, or just make sure you brush your teeth afterwards and like do a whole bunch of push-ups. That's what I do. All right. Anyway, I'll see you guys later. Have a good day.